The last video on trigonometry looked at right-angled triangles and the relationship between the angle in a triangle and the ratio of a pair of sides, such as opposite over hypotenuse, the sine ratio, adjacent over hypotenuse, the cosine ratio, opposite over adjacent, the tangent ratio, memorised as SOHCAHTOA. Given two sides, you could work out an angle, or given an angle on this side, you could work out another side. What we are going to do in this video is look at three-dimensional situations where you can apply trigonometry. In particular, we'll take common 3D shapes and finding an angle given two sides. So here are some common shapes: the cuboid, square-based pyramid and cone. And here are some of the right-angled triangles that you can get from these shapes. So in the cuboid, the blue dotted lines are face diagonal, and with two sides it makes up a right-angled triangle. The red line is a space diagonal, and together with a side and a face diagonal, it makes a right-angled triangle. In this square-based pyramid, the blue triangle has a face diagonal, a sloping side, and half a side, making a right-angled triangle. And in red, it's got a face diagonal, the solid red line, a height, the dotted red line, and half a side, or equivalent to half a side, the dotted line here. Also in the square base pyramid, you have a face diagonal here in the base, and two sides, making a right angled triangle, or here, a sloping edge, a height, and half a face diagonal. And in the cone, this is the sloping height, the solid line, the height, the dotted line, and a radius, the dotted line here on the circle. So these are all examples of right angled triangles in three-dimensional shapes. The angle between a line and a face, this is a line and a plane. A plane is a flat surface. So there's a line, it's hitting this plane at a certain angle. If you imagine shining a light above the plane, so the light shines and it hits the line here, casting a shadow, the blue dotted line. The angle between the solid black line and the dotted blue line is the angle between the line and the plane. So applying this to this cuboid, there's a space diagonal, and it wants the angle between the space diagonal, this line, and the face ABCD, that's like the plane, flat surface. There's the projection on the plane, like the shadow, that green line. So the blue line has a shadow of that green line, and the angle between the two lines is the angle we're after, the angle between the line and the plane. Now you've met face diagonals and space diagonals if you've looked at the videos on Pythagoras' theorem. This very same diagram was used. So if we want this angle, we need to know two sides. We've got one of them 40. We need another side. We can't get the blue line quickly, but we can get the green line because on the bottom there's another right angled triangle. So there's the blue triangle. We're after the angle, so we want to apply trigonometry here. But for the bottom here, to get AC, one of the sides of the blue triangle, we can use Pythagoras. We've got two sides and a right angle, so we don't need trigonometry. It's Pythagoras we need. So we apply Pythagoras' theorem to get AC, and then we can use trigonometry. So there's the green triangle. AC squared is 24 squared plus 18 squared. 24 24s and 18 18s. Follow it through. It comes out in this case exactly 30. Of course, it wouldn't usually be an exact answer. And that AC is 30 on the blue triangle. And now we want to work out angle A. 40 is opposite to it, and 30 is next to it, it's the adjacent. We don't have the hypotenuse, it's blank. So opposite over adjacent is tangent ratio. Tangent ratio is 40 over 30. Instead of dividing 40 over 30, you could simply inverse tan this. take the answer from the calculator and round it as appropriate. The angle we're after there was GAC on the diagram. So that's the angle between the space diagonal and the base ABCD. Second example, square base pyramid. What's the angle between the edge AE has the sloping edge AE and the face ABCD, that's the bottom. Again, with a light shining, the blue line has the dotted line as a shadow. The angle between them is the angle we're after. And we drop a height down this black dotted line to make a right angle with AC, and we've got a right angle triangle. However, we've only got in this right angle triangle one side, the 4 centimetres. We could do with another side, we don't know the height. We could get AM because it's half of AC, and AC can come from the bottom triangle, which is right angled. The bottom triangle is 4 by 4 and it's right angled at corner B. So there it is. AC squared equals 4 squared plus 4 squared. Pythagoras, follow that through. It comes out at 5.656 and so on. That's the whole of AC. AM's half of it. So we divide that by 2. And that's AM. AM here is roughly 2.8. Now we've got this triangle which has the black dotted line, the height, half of the blue dotted line, AM, and AE, the sloping edge. So that's what the triangle looks like. We're after angle A. We know the adjacent, the one next to the angle, and we know the hypotenuse opposite the right angle. Adjacent hypotenuse is cosine ratio. So we apply the cosine ratio. We're using previous answer unrounded to keep everything accurate. Slight rounding here can knock the angle out quite a bit. So you would work that out. Inverse cosine it, and it'll come up with exactly, in this case, 45 degrees. There's no rounding involved. It should be bang on 45 degrees, unless you've rounded a previous answer and it's knocked the answer out. So as long as you didn't round, it would be exactly 45 degrees. So that's 2 examples on the angle between a line and a plane, applying trigonometry in 3 dimensions. The next case, the angle between 2 faces. That's like between 2 planes. If one plane intersects another, there's a line of intersection here in red. What you do is you draw a line on each plane, meeting at a point on the red line, and they have to be at right angles to that red line. So it's a wee bit difficult to draw, but here it is. So on the sloping plane, this blue dotted line makes a right angle with the red line. On the orange plane, this blue dotted line makes an angle with the red line, which is 90 degrees here. That's the perpendicular part, and they meet at a point, and it's the angle between the 2 dotted lines. Now that's the angle between 2 planes, 2 faces. Here's an example. Here's a square base pyramid. What's the size of the angle between faces EBC, that's this triangle on the right, that face, and ABCD, which is the base. So what we need is a line on each face, meeting at the line of intersection BC. BC is the intersection between these 2 faces, and they make a right angle with BC. Each of them has to make a right angle. So there's EP, it goes out to the midpoint of BC, and it makes a right angle. And this blue dotted line lies in the plane ABCD, and it makes a right angle with BC. So they're both right angles to the line of intersection, and they meet at a point P, and it's the angle of turning between the dotted line and the solid line. Now, so far, we have to work out this angle, but we need it to be in a right angle triangle. If you drop a height, there's a height, E. This point here, I'll be calling M in the diagram. I've not put it in here just because it was getting rather cluttered. So this dotted line will be EM, and it makes a right angle with this other blue dotted line until you get a right angled triangle. Now, first, because you don't know the height, you don't know the blue sloping line, all you know is this position, which I'm calling M, out to P is half a side, it's 2, so only one side. So EP, sloping side, is what we need. It's on this face. So PC there was 2, half a side. Pythagoras, EP squared is equal to 4 squared minus 2 squared, and then you follow it through. I've stopped at root 12, don't want to work out in the calculator because I want to keep everything accurate. So EP is root 12. So there's a triangle from E to P, and the point we're going to call M now. And the blue line there is root 12. There's a triangle. I've called this point here M, just to label it. We're after the angle EPM there. And there's a root 12 that we just worked out. There's half a side. So this line here was half of 4. We've now got two sides. We want the angle. It's the adjacent and the hypotenuse we've got. So root 12 is opposite the right angle. 2 is right next to the angle. Cosine's adjacent over hypotenuse. Cosine of the angle is adjacent to over hypotenuse root 12. You could just simply put in the calculator inverse cos and then put in the fraction button 2 and root 12 and get the answer. There it is. So you don't even have to work out what 2 divided by root 12 is in the calculator. Just put that into the calculator. Out comes an unrounded answer, and you can then round it off. So that's the angle between two faces. Quite complicated, a wee bit tricky. There's a worksheet, and it will involve angles between a line and a plane and an angle between two planes. So that's between a line and a face, or between two faces. They can be downloaded. The worksheet can be downloaded if you use a link in the description, and it will have the answers with it. So that's one question there. Cuboids. This is square base pyramids. And then again, this is between two faces. Square base pyramids. So I'll have the answers with it. There's also a set of notes. And if you download the notes, it's got these examples on it, so you don't need to copy anything down. So if you use a link in the description, that's the worksheet you can download as a PDF. 12 questions, and it's got the answers. And set of notes. It covers all the trigonometry videos on right angled triangles, and it's got what we've just had in this video with the examples. Hope you found the videos useful.